All right, let's pull back the curtain on a truly foundational piece of the internet: consistent hashing. It's this beautifully simple idea that, well, it secretly powers some of the biggest services you use every single day, and you've probably never even heard of it.
I mean, have you ever really stopped to think about it? How do services like these stay online when servers are constantly being added or moved or just failing? Well, it turns out the answer is a surprisingly clever concept, one that was designed to bring order to exactly that kind of chaos.
So, to really appreciate just how brilliant consistent hashing is, we first have to understand the absolute disaster it was invented to prevent. It's a problem that's often called the rehashing catastrophe.
Okay, so the most obvious way to spread requests across a bunch of servers is with some really simple math, right? You take a key, say your user ID, you turn it into a number, and then you use the modulo operator. You just divide by the number of servers and see what the remainder is. That remainder tells you exactly which server to use. It seems clean, easy, and it looks like it works perfectly. And you know what? For a fixed number of servers, it works like a charm. With our 3 servers right here, all the user keys are distributed nice and evenly. Everything is balanced. The whole system is happy. For now.
But, and this is a huge but, this is where that simple, elegant approach reveals its fatal flaw. Because what happens the moment you need to scale up and add a new server? Or even worse, what if one of them just goes down?
Yeah, the entire system is just thrown into total chaos. That neat, perfectly balanced world we just had, it's gone in an instant.
And this is the critical point. The second we add that 4th server, the number we're dividing by in our little formula changes from 3 to 4. And that one tiny change completely scrambles the results for almost every single key. Just look at user C and user D. They're now suddenly supposed to be on completely different servers. And that is the rehashing catastrophe. At scale, this is an absolute disaster. You're talking about a massive amount of data that has to be moved instantly. All your caches become useless because the data they're holding is suddenly in the wrong place. And this triggers a tidal wave of requests hitting your main database, which can easily overwhelm it and bring your entire service grinding to a halt.
So what's the fix? How do you build a system that can scale without, breaking? Well, back in 1997, some very smart people at MIT came up with a far more elegant approach. They called it consistent hashing, and the core idea is just beautiful in its simplicity. Let's design a system that minimizes disruption. The goal is that when the number of servers changes, only the absolute smallest number of keys possible have to find a new home. The big breakthrough here is a mental shift. You have to stop thinking about your servers as a numbered list, one after the other. Instead, imagine all the possible hash values laid out on a giant circle, kind of like a clock face. This is the hash ring. Okay, so here's how it works. First, you take each of your servers, we'll just call them A, B, and C for now, and you hash their names, or maybe their IP addresses, to figure out where they live on this ring. Now, how do you know where your data goes? It's actually super simple. You take any piece of data, you hash its key to find its own position on the ring, and then you just walk clockwise. The very first server you run into, that's the one responsible for that key. That's its home. All right, now for the moment of truth. Let's see what happens if server C suddenly goes offline. Remember, this is the exact scenario that caused a total catastrophe with our old method. With the hash ring, the result is night and day. The only keys that need to move are the ones that belong to the failed server C. They just continue their clockwise journey and land on the next available server, which, in this case, is server A. And this is the magic part. The keys that were already on server A and server B, they don't move at all. The disruption is contained. I mean, the difference is just staggering. When a server is added or removed from a system with n servers, only about 1/nth of the keys need to be relocated. It is a massive improvement that makes it possible to scale systems without that constant, catastrophic reshuffling.
Okay, so this is a huge improvement, but it's not perfect, not yet anyway. While we've solved the big rehashing problem, we can accidentally create a new one, an unfair distribution of the load. So let's look at how we can refine this even further. Just think about it. Since we're placing servers on the ring based on a pretty much random hash, what if you get unlucky? What if they happen to cluster together? One server could end up being responsible for a huge arc of the ring, while the others get these tiny little slivers. That would lead to a very unbalanced and very unhappy system. The solution for this is an absolutely brilliant little trick called virtual nodes. So instead of giving each real server just one spot on the ring, you give it lots of them, multiple aliases. So your physical server A might show up on the ring as A1, A2, A3, and so on. By doing this, you're effectively breaking up those huge, unfair gaps on the ring, and the result is a much, much more evenly spread workload across your actual machines.
So, let's bring this all together. Why does this algorithm, something cooked up in the 90s, matter so much today? Well, its impact has been absolutely profound. I mean, just look at the journey this idea has been on. It started as an academic paper trying to solve website hotspots. Back then, they called it the slashdot effect. And then it became a core component of Akamai's massive CDN. Then it was foundational to distributed databases like Amazon's Dynamo. And today, well, today it's just everywhere. And I'm not kidding, the list of technologies that rely on consistent hashing is basically a who's who of the modern internet. From massive databases like Cassandra and DynamoDB that store petabytes of data, to chat apps like Discord handling millions of people talking at once, to the CDNs that are delivering this very explainer to you right now, this algorithm is a critical piece of the backbone that holds it all together. Okay, so let's boil this all down. After all that, what are the key benefits? What makes consistent hashing such a powerful and enduring tool for anyone building large-scale systems?
Okay, first, and this is the big one, you get minimal disruption. That's the key to stability. And that stability, in turn, leads to high availability because your system can just gracefully handle servers coming and going without a total meltdown. And finally, all of this together is what enables true horizontal scalability. It's what allows services to grow to almost unimaginable sizes just by adding more machines. So really, the next time you're seamlessly streaming a movie or loading a web page in an instant or chatting with your friends on some huge platform, just take a second. You'll know about the invisible but absolutely essential engine humming in the background. It's the elegant, mathematical dance of a hash ring at work, keeping our digital world running smoothly.